optical or taped survey is admittedly low tech, but even in the age of LiDAR, photogrammetry and GPS, it's still an effective and accessible way of recording earthworks and other field remains, and, more importantly, of understanding them. Now, the same technique can be used to record standing buildings too. So, how is it done?
The first step is to carry out a detailed and thorough recce, or reconnaissance, not only of the area you've been asked to investigate, but also of the wider environs, just to check there's nothing crucial lurking just beyond the hedge. This is called a level 1 or walkover survey, and sometimes it may be all you need to do. In today's world, it can be tempting to just look at online resources like LiDAR, Google Earth and Street View. But you should resist that temptation because you run the risk of overlooking some really important factor that you will only find out about by visiting the site in person. By the time you complete your recce, you should be in a position to make all the key decisions about your next steps, the scale and extent of your survey, the equipment you'll need, health and safety issues, timing, and so on. That's assuming you think further work is needed at all, of course. A recce can sometimes be invaluable in saving people from overcommitting resources to a project that turns out to be a non-starter. For your recce to be effective, visibility on the ground needs to be fairly good, so the vegetation needs to be as sparse as possible. Consequently, you may well end up doing your recce in the winter or spring. Choosing the right time to do more detailed field survey is also really important. Working in woodland is easiest and most informative in spring, while moorland can often be off limits at that time due to ground nesting birds. Military ranges and farmland often have more unpredictable restrictions. Scale is a particularly important question. It's common to work at 1 to 1,000. In other words, 1 metre on the ground equals 1 millimetre on your plan. At this scale, most individual sites will be straightforward to publish on a printed page, and you can record fairly fine detail, which is usually sufficient to underpin your interpretation of the site. But particularly complex military or industrial sites may need to be recorded in more detail and therefore at a larger scale, such as 1 to 500. In other words, 1 metre on the ground equals 2 millimetres on your plan. You can always do small windows of survey at larger scales, perhaps even the scales commonly used in excavation, 1 to 50 or 1 to 10, if you want to record individual features. And for extensive landscapes, you'll need to sacrifice some of the detail in order to cover the larger area. A scale of 1 to 2,500 is often used. In other words, 2.5 metres on the ground equals 1 millimetre on your plan. This scale has the advantage of matching the standard scale at which the Ordnance Survey mapped most of the British Isles from the mid-19th century onwards. To summarise, a recce is a valid archaeological investigation in its own right, but it should also pave the way for future work, including more detailed field survey, geophysical survey, other remote sensing, and ultimately, excavation.
Doing the recce gives you an opportunity to think about your control network, a matrix of carefully chosen individual points that will act as a framework around which you can build your detailed measurements of the earthworks and any other features that seem relevant. At its simplest, for a small feature like an isolated Bronze Age round barrow or this First World War practice trench on the outskirts of York, a control network may just constitute 2 points with a single baseline running between them. A simple survey like this, which is internally accurate but not related to the map background, is called a divorced survey. You can use a compass to at least establish where magnetic north is, and, depending on where you're working, you may be able to use features that have already been mapped by the Ordnance Survey, such as building corners and fence junctions, to fix the positions of your own control points. But, for large or complex sites, you'll probably need to use survey-grade global navigation satellite systems or a total station theodolite to establish a network of temporary markers. That's 1.461. Try to be efficient and economical with where you place the points, but don't be too frugal or you will probably regret it at the next stage. Your control network can include building corners, foundations, gate posts, drain covers and so on, and these can also contribute to your detailed survey so that you kill two birds with one stone.
Okay.
You can use wax crayons or paint to mark individual fence posts, but don't mark so many that you will later struggle to work out which is which.
Up to 2.05.
You can also put in your own temporary markers at specific places that exactly suit your needs. Wooden pegs are an environmentally friendly option, but if you are working in fields where there are livestock, especially horses, be careful to hammer them flush with the surface to avoid broken ankles and the risk of prosecution. As the vegetation grows, your markers may eventually become difficult to see, but you should be able to relocate them, even several years later, by taking careful measurements from the plot of your control network. Surveying paths and trees will give you a rough guide. With earthworks, it's often best to hammer in a peg at the ends of linear features like banks and trackways, as well as at angle changes and intersections with other features. This enables you to work with the grain of the archaeological features. This will improve both your analysis of the earthworks and the metrical accuracy of your survey. It will also save you time and effort. Once you've plotted these points out at the scale you've chosen to work at, you're ready to go back into the field and start the next step, the detailed survey.
Okay, so do you want to tape or draw?
I think you know the answer to that one.
You're going to draw. Great, good, thank you.
Detailed survey involves systematically working across the whole site, plotting any earthworks you observe, regardless of whether or not you can make sense of them, as well as any other remains you encounter. As you're going along, it's often worth recording features relevant to conservation and management, such as scrub, animal burrows and erosion. Plotting the shallow pits left by fallen trees, the outlines of trenches dug by earlier archaeologists, and the holes left by illegal metal detectoring can all be highly informative. A Level 2 survey is a detailed record of the field remains. A Level 3 survey will involve follow-up research to interpret what you've observed in the field, using maps, aerial photographs, LiDAR, oral testimony, previous research, and literally any other source of information you can lay your hands on. This intimate and prolonged encounter with a site, ideally by the same two people working closely together throughout the fieldwork, will put you in the unique position of having scrutinised every detail of the earthworks. In terms of the analytical value of your investigation, this represents a massive improvement on just examining LiDAR or photogrammetric imagery on screen, where critical information such as stratigraphic relationships and changes in vegetation texture are usually difficult to detect and interpret. And of course, the information you may gain from observing small artefacts like worked stones, pottery and so on is inevitably going to be missed by remote sensing techniques. There are several different ways of conducting a graphical survey. You can use a plane table, although this can be fairly backbreaking and the kit required is increasingly difficult to get hold of. Pace and compass survey can be effective in dense woodland where not even LiDAR can penetrate. If you have access to high-resolution LiDAR data, it's possible to use the imagery as a ready-made plan of the earthworks, to which you can add your own interpretative notes. And of course, you can replicate the approach of low-tech taped survey by using GNSS or TST to map lines and points. This immediately gives you a digital and three-dimensional product, but can take far longer than simply using a ruler, pencil and paper. Anyway, today we're going to concentrate on one of the simplest and most effective taped survey methods, a technique called baseline and offset.
As I mentioned before, a baseline is simply a tape stretched straight between 2 points. This is represented on your plan by a straight line of the same length, drawn fairly faintly and always drawn with a ruler. The 2 points can be any points whose locations you fixed with the GNSS or total station, or that the Ordnance Survey has mapped before. Ideally, your 2 points should be more or less level with each other, because a steep slope will noticeably change the distance when plotted in plan. If one point is much higher than the other, it probably means you didn't get your control network right. But never mind, you can zero your baseline at the higher of the 2 points and pull the tape horizontal to compensate for the difference. Even on level ground, to get a long baseline dead straight, you may need to set up a wave motion and bounce the tape into position, perhaps hopping it over sticks or clumps of nettles. Make sure you're certain which point it is your baseline is heading for. Marking all your points with ranging rods or bamboo canes can reduce confusion, but if you're uncertain, it's always wiser to measure the distance between the two and confirm that distance against the scaled drawing, rather than discover too late that you've been using the wrong point.
Okay, so which baseline is it? I've got two here. One's 78.5 and the other is 69. Yeah, that's it. That's a little bit more.
Your baseline doesn't even have
Back
to
the
reach
other way.
all the way to the second point, as long as you're certain which it is.
Pretty good.
If you hold the tape out to one side of your body, your partner will be able to clearly see the target point beyond you and line up the baseline perfectly. When communicating, especially over long distances, make sure your hand signals are clear. Left hand for left, right hand for right.
9 meters.
Next, you make your offset measurements. The offset is a tape running at right angles to your baseline, starting from a known point on the baseline, and again represented on the drawing by a faint line drawn with a ruler.
5.2.
If you need to plot the corner of a building, the end of a wall, or a find spot, the easiest way is to zero your offset tape at the point you want to fix and then extend it back to the baseline. Swinging the offset tape in an arc from side to side will then allow you to tell the shortest distance, which must be a right angle.
15.9 gives 2.6.
When surveying earthworks though, if you zero your offset tape at integers on the baseline tape wherever
Top of the
possible,
ridge.
for example 4 meters
2.2.
exactly, this will make it easier, quicker and more accurate for the person
baseline.
responsible for doing the drawing. If you're dealing with a linear feature, like a bank and ditch, you can pick up several different measurements along the line of the offset,
3.7.
which speeds the process up enormously,
For the
especially if your baseline is running close to the linear feature and parallel with it.
4.
This is what we mean by working
Top
with
of
the
the
grain
ridge.
of the earthworks.
1.4.
In these circumstances, where you're working close to a feature and measuring across it in a more or less perpendicular way, it's usually acceptable to judge a right angle by eye. But if you find that you need to measure to a point a long way from your baseline, you will need to measure your right angle more accurately. So, use a bit of simple Pythagorean maths to make sure you've got it right. Up to about 8 metres away, a 3, 4, 5 metre triangle will work fine. But if it's a really long way away, you will have to construct, say, 30, 40, 50 metre triangles to ensure your offset is accurate. This, of course, is in essence the same technique used to set out grids for geophysical surveys and field walking. It's also worth saying that if a perpendicular angle doesn't suit what you want to measure, you can always tape from a known point on the baseline towards another fixed point. The scaled drawing itself will give you the correct angle. And if you're surveying a small circular feature, for example, this low mound that seems to be a Victorian flower bed, one effective technique is to fix a wooden peg at its centre and use that as the 0 point for a series of radial measurements, starting with a simple cross and then bisecting each quadrant at 45 degrees.
Sure.
So, what is it you're actually going to measure? Well, it may surprise you to learn that it's not necessarily the highest or lowest points of the earthwork. It's actually the points where the gradient change is sharpest for each slope that makes up the earthwork. The person on the drawing board then marks each of these tops and bottoms with a tiny dash along the offset line, slightly longer for tops, barely more than a dot for bottoms. Once a series of them have been plotted, the marks can be joined together with a hand-drawn line, like a dot-to-dot drawing, but with smooth curves that reflect the fluid form of the earthwork. Later, hashes can be added to show the strength of the different slopes. Changes of gradient are easy enough to judge with a crisp slope, like the sides of this Roman defensive ditch. But what about when the earthwork is slight and variable, and maybe meandering around a little? In those circumstances, looking down at your toes can be misleading. The person doing the taping should look to either side of themselves to get the general trend of the changing gradient, and then try to be consistent in picking the same line on all the subsequent measurements. The person on the drawing board can also be helpful, because from slightly further away, changes in gradient can sometimes appear more obvious. Different phases of activity, for example the recutting of a ditch or the enlarging of a mound, can be represented by subtle changes of gradient within what may at first appear to be just a single slope. These changes, known as breaks of slope, can be extremely revealing, so always be on the lookout for them. How far apart do you need to take the offsets, and how accurate do the measurements need to be? Well, both of those depend on what you're measuring and on what scale you've chosen to work at. For example, if you can see that a wall runs dead straight for 100 metres, there's absolutely no point in taking 20 offsets to prove that. Fixing the start and end points of the straight section will be sufficient. On the other hand, rigidly continuing to take offsets every 5 metres when an earthwork is very variable in form, or when it's intersecting with other features, runs a high risk of misrepresenting the changes that do exist. As a general rule, it's helpful to take offsets just before and just after intersections with other features, because those intersections are often where changes in form take place. And in terms of accuracy, at the normal scale of 1 to 1000, measuring to the nearest tenth of a metre will be sufficient, because it's almost impossible for the person doing the drawing to draw finely enough to differentiate tenths of a millimetre, even using these special super precise German pencils and sharpeners. So don't get too worked up over whether a top is at 11.6 or 11.8 metres. Such minute differences are unlikely to change the outcome of your analysis.
And then this little patch of erosion.
If you find yourselves repeatedly needing to represent features less than half a metre wide, it probably means you chose the wrong scale at the end of your initial recce. By the same token, if you're working at a smaller scale, for example 1 to 2500, it will be very difficult to depict anything smaller than 1 metre wide, which is why the depictions of archaeological sites on Ordnance Survey maps may seem very basic. And be cautious about committing yourself to a survey at 1 to 500 scale or larger. It will entail taking more than twice as many readings and being ultra careful about the accuracy of every measurement.
Above all, both the person doing the taping and the person doing the drawing should be looking for patterns in what they're seeing and attempting to interpret what they're observing as they're going along. If the form or condition of an earthwork changes, what has happened to bring about that change? Has another feature, perhaps of earlier or later date, had an impact?
Looks more like a Second World War weapons pit to me.
For this reason, although it may be tempting for the taper and the drawer to keep swapping roles, you can often get a better result by keeping the same role all day or even throughout the entire survey. This should not relegate the drawer to a mere passive supporting role. Their role is also to voice insights gained from the emerging drawing, to question the observations made by the taper where appropriate to argue, to ask for additional measurements where necessary, and generally to act as a teammate. Establishing a good working relationship based on dialogue is absolutely critical to the interpretation of the field remains and to the rapid and efficient completion of the fieldwork.
Sorry, I'm absolutely covered in ladybirds. Just a moment.
When you've eventually finished your survey, take a leisurely walk over the whole site with the plan you've made. Does what you've drawn still look like what you can see on the ground? Have you remembered to annotate which slopes are stronger and which are weaker, so that you can represent them correctly on the publication drawing? Everyone makes mistakes from time to time, especially when it's cold, windy and wet, and it's better to spot those mistakes and correct them before you pack up and head for home. And it's often this final walk around, discussing the finished plan with your teammate, that crystallises an interpretative narrative. Feel free to scribble notes on the plan to remind yourself, or to record your observations and ideas on your phone. Taking photos can also be helpful sometimes, but unless you're lucky enough to be present in perfect light conditions, earthworks seldom appear clear on film. For that reason, if you do get perfect light at some point during your fieldwork, don't hesitate to drop your tape measure immediately and capture any images you might want to use in your report. By the time you leave the site, the structure of your report should already be starting to take shape in your mind.
You can draw upon information from a very wide range of sources to add value to your field survey. Old maps, aerial photographs and historical documents are often of particular importance in interpreting what you've recorded. Compiling this information and perhaps reviewing LiDAR imagery or earlier depictions of the site can often raise new questions that you didn't consider during your fieldwork. If you find that you want to re-examine or even resurvey specific features, there is no problem with doing so, but you should never be tempted to adjust your findings to match the new information. For example, if an antiquarian reported that he dug 2 trenches, but your survey has identified 3, you should not try to eliminate one of your 3. If an aerial photograph shows a parch mark that was not visible at all during your fieldwork, by all means mark it on your plan, but do not imply that you yourself could see it on the ground. On the other hand, if geophysical survey shows no sign of a ditch that you have detected as a slight earthwork, do not lose confidence. Excavation may eventually prove you correct, but even excavation is not always infallible.
Drawing up your field survey, plus any interpretative plans based on it, is the next step. You will usually need to produce a written report too, its length and complexity depending on how much your plan speaks for itself.
Finally, remember that people outside academia will want to know about your conclusions. People often equate archaeology with excavation, but in the end they find that they love field survey because the evidence is there for all to see and because the recording method is relatively simple. Plus, the conclusions that you can reach through doing field survey are often much more dramatic and wide-ranging than those that small-scale excavations will allow. There again, if your ideas, your conclusions, are not in accord with those of excavating archaeologists, don't be afraid to assert your views.
you.